Hi everyone, and welcome back to another episode of Science. We're actually starting a new season of Science today, specifically called Electromagnetism. Now, electromagnetism explains the relationship between electricity and magnetism. It was Michael Faraday who first started to discover and explore the link between electricity and magnetism. You can actually create magnetism using electricity, and you can create electricity using magnetism. And in this season of Science, we're going to explore how those two things can interact with each other. To begin our journey, we're going to have a look at magnets and magnetism. And as we go along, we'll have a look at how magnets interact with electricity specifically. If you load up the PowerPoint and you click into this video here, you'll get 9 amazing magnet gadgets. It's pretty cool, so check it out. Okay, let's begin. The earliest magnets were found naturally in the mineral magnetite, which is abundant in the rock type lodestone. So you might have heard of the word lodestone before. These magnets, lodestones, were used by ancient peoples as compasses to guide sailing vessels. Think back to a time when there was no technology. There's no Google Maps, no GPS or anything like that. Sailors would use the stars and constellations to help guide them, or the position of the sun to help guide them. But what if, it's nighttime, there's clouds in the sky, you see nothing but water around you, nothing but ocean around you, no landmarks. I mean, how do you navigate in those circumstances? Pitch black, no stars, just water around you. Well, they needed compasses as well. Now, these sailors, they didn't know how compasses worked. And look, chances are you don't know exactly how a compass works either. But you will by the end of this season. You will by the end of this topic. To summarize, the needle of the compass essentially aligns itself to Earth's magnetic field. Earth is actually like a giant bar magnet, and the little compass needle is aligning to the magnetic field of Earth. And we're going to explore Earth's magnetic field as well. Pretty cool. Let's continue moving forwards. So we have 3 naturally occurring elements that can produce magnetic fields naturally. We call these ferromagnetic substances. These are substances that can display the property of and interact with magnetism naturally. These are iron, cobalt, and nickel. So if you were to dig out of the ground 2 chunks of iron, chances are they will attract each other. Chances are they will be naturally magnetic. And that's unique to these 3 elements. And there's important reasons as to why that is. It's to do with the electron configuration and the electron pairs and spins and things like that. It goes beyond the level of what we're studying in Year 10. But please feel free to jump on the YouTubes and discover the more complex workings of how magnetism is produced on a quantum level, that is. So iron, nickel, cobalt. Why are these substances naturally magnetic? What is happening in ferromagnetic substances at the atomic level? Well, here we have groups of atoms, and we call these groups of atoms domains. Now, normally these domains or groups of atoms are scrambled. They're all facing different directions. And if they're facing different directions, you don't produce a magnetic field. Your substance is not magnetic. However, if you can start to align those domains to face the same direction, if you can align those atoms to face the same direction, you can start to produce a magnetic field. You can make your substance magnetic. If you can align all of the domains to face the same direction, you will have a strong magnetic field or a strong magnet. The more aligned they are, the stronger it is. Domains are large areas in ferromagnets in which the magnetism of the individual atoms and molecules are all aligned in the same direction. Let's have a look at these two diagrams. Which one would display magnetic properties? So the top one or bottom one? I'll give you about 5 seconds. If you said the bottom one, you would be correct. You'll notice that these domains are more lined up than these domains. Because these domains are all scrambled, you're not going to produce a magnetic field or a magnetic force in this substance. But this one here, most of them are lined up to face mostly the same direction. So this substance, this ferromagnetic substance, could potentially produce a magnetic field and become magnetic. We've got two types of magnets, hard and soft ions, we call them. Now, a hard magnetic material, it can start off with its domains all scrambled up and misaligned. If you introduce another external magnetic field to it, this magnet can force the domains to actually change direction. And it can force at least some of the domains to face the same way, to face the same direction. It can force them to align. When you take away the magnet, a hard magnetic substance, a hard ion, the domains will stay aligned. Pretty handy. We also have soft magnetic materials. Once again, the domains can start scrambled. You introduce an external magnetic field, like another magnet, that'll align the domains, making this substance magnetic. However, when you take away this magnet now, because it's a soft ion, the domains don't stay aligned. Over time, they scramble up. You can actually do this at home. If you've got a permanent magnet and, say, a paperclip, you can rub the magnet against the paperclip, and that magnet will align the domains of the paperclip, making the paperclip a temporary magnet. You may be able to pick up 1 or 2 additional paperclips using it, but over time, it'll lose its magnetism. There's a special method to create a hard magnet, to create a permanent magnet. You've got to heat it up and align the domains, cool it down, but we don't need to go into those details. So here are our notes for hard and soft ion. For a hard ion, the domains align, and you can make them stay aligned. They tend to stay aligned, and we call these permanent magnets, so we'll use these in class. Soft ions will actually make soft ions, or we'll make temporary magnets in the classroom as well. We can align their domains using another magnet or another magnetic field, but the domains don't stay aligned. When you leave them alone, the domains tend to scramble up on their own. They can't stay facing the same direction. And when you align those domains, the magnetic field is magnified by 100 or even 1,000 times. So the more you can align those domains, you can create a pretty powerful magnet. In class, we'll use an iron nail and a permanent magnet to create a temporary magnet. Now this iron nail here is a soft ion. Its domains inside of it are all scrambled up. They're all facing different directions. However, in a permanent magnet, all the domains are aligned. They're facing the same direction. And so a permanent magnet has a magnetic field around it. It produces a magnetic force. When you move this permanent magnet close to the iron nail, the domains that are aligned in the permanent magnet, okay, and they flow in this direction. So the magnetic field flows around the permanent magnet, and the domains that are lined up within this magnet here are facing one direction, like so. When you bring a soft ion next to it, this permanent magnet forces the domains in this soft ion to also face the same way, so they become matching. And now that you've got your domains lined up with each other, this iron nail here has become a temporary magnet. And so the two magnets attract each other. If I was to take away this iron nail, the domains would stay lined up for a temporary period of time, but over time, the domains will begin to scramble up again. And as it scrambles up again, this iron nail will lose its magnetism. And we can create this in the classroom as well. Well, how do we destroy magnets? You can unalign domains to be in random direction if you expose it to a constantly changing, stronger magnetic field. So you keep flipping a magnetic field, keep changing its direction, and you can scramble up the domain of another magnet, the domains of another magnet. You can also bash it. Strong physical impacts can physically scramble up the domain. So treat the magnet in the classroom gently so that it can retain its magnetic properties. You can also heat the object above its Curie temperature to break those bonds and scramble up the domains. I've got a video here that goes into a little bit more detail, so if you want to click on this video, learn a little bit more about how to destroy a magnet, it'd be good. Click on it. Well, a common question I get is, what if you break a magnet in half? If you were to break a magnet in half, you don't end up with a north piece and a south piece. You end up with two new magnets, and each new magnet has its own north, its own south, north and south. I can break this one into two again, but I'll just end up with two new magnets, smaller, but they'll each contain their north and south pole. And these poles will come into play in the next episode of science. And these poles are important because it determines the direction of the magnetic fields. But that's for next episode. For now, we'll move into our private study. So we'll do experiment 1 in class. I'd like you to do question 1A to D from your workbook and make a start on your Education Perfect Magnetism module. Thanks for joining me in this episode of Science. I hope it was helpful. If you've got some questions, leave a comment below or come and ask me in class.